Welcome everyone to the lecture on Cartesian tensors. In the last lecture, we have studied what indicial notation is, and we have seen its application on vectors and vector operations. In this lecture, we will study the same phenomena of using indicial notations. However, we will also define what formally a tensor is, what is its relation to a vector, and then perform indicial operations on tensor additions, or basically tensor operations. All right. So this is what we have seen last lecture, saying an nth order tensor maps an n-1th order tensor to a first order tensor. This is like the generic definition. And then we have also said vector is a first order tensor and a scalar is a 0th order tensor. And what we know as stress and strain from mechanics of solids are essentially symmetric second order tensors, right? So now let us be specific to second order tensor. And a second order tensor is basically a function mapping from an Euclidean space to the same Euclidean space. All right. So, and specifically that function is also a linear transform. Now, what is a Euclidean space? Any vector that we consider, whether it is displacement, electric field, magnetic field, velocity, acceleration, all of them are vectors in the three-dimensional space. So that three-dimensional space is referred to as the Euclidean space. So a vector we indicate always with an under arrow, right? An under bar or an under arrow. So this belongs to the 3D space. So a second order tensor is a linear transform from a Euclidean space into itself. So tensor we will always represent with two arrows as shown here. Vector will stick to a single arrow. Tensor will represent it with two arrows below the variable. So that's how we will distinguish between vectors and scalars, vectors and tensors. And linear transform specifically, what does this linear transform mean? Linear transform basically means the following. If V and U are two vectors which belong to E3, so essentially your A is taking some vector V and it is giving out another vector A. That's what we are saying. It is mapping from an 3D Euclidean space to the same 3D Euclidean space. It is taking a vector as an input and it is taking the output is another vector. So that is what this statement means. Now let us look at what does this linear transform indicate. So if there are any two general vectors U and V belonging to the Euclidean space and a particular scalar alpha, then if f of u plus v is f of u times f of u plus f of v, and a function of the scalar times the argument is same as the scalar multiple of the original function, then such a transform is a linear transform. And since we are talking about second order tensors, I have directly used the tensor A. So tensor A acted on the sum of vectors u and v is same as tensor acting individually on the two vectors and the sum of it. Right? And likewise with the scalar variable. So this is essentially representing the linear function. We are saying a second order tensor is a linear function from a 3D Euclidean space to itself. It is mapping a vector to another vector. That's what it is doing. So geometrically, what does it mean? Geometrically, this is what it means. If you have two vectors, u and v, or for that matter, any number of vectors, let's consider u first. This vector u, a tensor A is acting on it, and it has become a different kind of arrow. Originally, it was u, and that vector got stretched or compressed. So basically its magnitude is altered and also its direction is altered. So it has been rotated in 3D space and its magnitude also is changed. So a vector, a second order tensor transforms a vector in magnitude and direction. The same thing has been done for V. Okay, so that is what a second order tensor does to a vector. Okay, that it can act on a scalar as well as a vector, and this is what it does. It alters the magnitude and orientation. And orientation is not, see, although we are showing it on 2D space, you have to remind yourself that V and U are vectors in 3D space. so is the tensor associated with that corresponding ready space, right? Likewise, that addition U and V can be added using parallelogram law. So you know that this is also V and this is U. Likewise, the transformed vectors AU and AV, further similar addition can be done. So geometrically, this is what it means. A tensor is acting on a vector and changing its magnitude and direction. Okay, it's purely mathematically speaking. And then we can also look at what it is actually specific to, whether it is stress or strain that we discuss. All right, I hope the idea of rather the geometrical context of a second order tensor is clear. Right. First, the dyadic product. Before we jump into tensor operations and adding tensors or doing any mathematical operation on tensors, a tensor is a second order tensor is nothing but a two-dimensional matrix. A vector was a column matrix, right? Vx, Vy, Vz. This is basically a matrix, or specifically a column matrix of 3 rows and 1 column. Whereas a tensor, a second order tensor, is represented by a matrix which is of size 3 by 3. It need not be symmetric. A second order tensor need not be symmetric. So before we go to tensors, so let's visit this dyadic product. But you should have an idea that a second order tensor is represented by a matrix, and you know a vector can be represented by a column matrix. You guys are already familiar with a dot product and a cross product. Dot product is indicated by 8 dot B and cross product is indicated by A cross B. But this is a new kind of product called dyadic product, and this is designated by A cross, and the cross is encircled. Or simply, we will put it as A, B. Let us not join these two underlines. This is something which has happened to the typeset, but let us write it as vector A and immediately followed by vector B. No dot or no cross symbol in it. If there is no symbol, we will consider that as a dyadic, or also called as tensor product. Okay. Some mathematics books also refer to them as outer product. Inner product is the dot product. Outer product is the tensor product. Okay. But how is this defined? This is how it is defined. Consider any vector U belonging to the 3D space. This is how it is defined. This is the dyadic product. This is the short form notation which we will stick to. And the result of it is this. You're taking the first vector and you're taking the second vector, dotting it with the first one, and then multiplying with the first vector. That is how a dyadic product is defined. Okay, for any vector U. So if we consider the standard vectors E1 and E2, what is E1? E1 is basically the unit vector along x-axis. E2 is the unit vector along y-axis. Right? Now, if at all I have to take the dot product, the way we write it is E1 dot E2. And the way you perform it in mathematical operations is E1 transpose E2. Right? So E1 transpose is a matrix of size 3 by 1. E2 is a matrix of size 3 by 1. So essentially you get a scalar which is 1 by 1, which is that represents the dot product. So E1, E2, this E1, E2 is basically E1 dyadic product with E2 is can be written in matrix form in this type. E1 has a size 3 rows, 1 column. E2 has a size 1 row, 3 columns. And so this gives me a matrix of size 3 by 3. So this is what we are doing. This is 3 by 1 and 1 by 3. I'm sorry for this typo. It is this. Right? 0, 1, 0. Because we are doing with E2 and not with E1. So 0, 1, 0. And which means the matrix will get altered. Please do make these changes. This is 1 into 0 will be 0 and 1 into 1 will be 1. So this is the corresponding change. All right. So it'll have 0, 1, 0, 0, 0, 0, 0, 0, 0. So this is the corresponding E1, E2. If you look at E1, E1 tensor, you will get 1, 0, 0, 0, 0, 0, 0, 0, 0. If you look at E1, E3, right? So you'll get 0, 0, 1, 0, 0, 0, 0, 0, 0, and so on. If you have E2, E3, basically second row, third column. So 0, 0, 0, 0, 0, 1, 0, 0, 0. Like that, you can have 9 independent such components. Right? So effectively, your A is nothing but A is nothing but Aij, Ei, Ej. All right, your matrix or a second order tensor is nothing but Aij, which is the scalar. This is the scalar. This combined is the dyadic product. You know now what E1, E2 is, E1, E1 is, E1, E3 is, E2, E3, and so on. Right? So a second order tensor is nothing but a dyadic. It is written as a sum of dyadics, or in effect a dyadic itself. Right? So it is which is what I've tried to show. The sentence here is dyadic product of two vectors gives rise to a second order tensor. This is what you have seen in this particular slide. Take any two vectors and you take the dyadic product, it leads to a second order tensor. You want to keep the same order of the tensor, you take a cross product. You want to reduce the order, take a dot product. You want to increase the order, take the so-called dyadic or tensor or outer product. All being the same. Right? This is what we proved in the previous slide, that dyadic product of two vectors U and V gives a second order tensor. So this is the corresponding notation. Some books may write this as U circle V. We'll simply say UV because that symbol is not such a pleasing one. Right? And you know, if you have to write it in components, this is the corresponding scalar component of the element Aij. And this is the corresponding dyad. Right? And the components are basically this. As I said, this is the component. This is the dyad. And in matrix notation, this is what it is. Okay. Aij is Ui Vj. If you see A21 is U2 V1. U2 V1. All right. So a dyadic product of two vectors leads to a tensor. Dot product leads to a scalar. Cross product leads to a vector. Dyadic product leads to a tensor. Right? Now, if E1, E2, and E3 be an orthonormal basis of E3, which means the second E3 is the Euclidean space, here we are not specifically saying that E1 is the unit vector along I hat, J hat, or K hat. Need not sometimes, because you can choose any three orthonormal vectors as the corresponding basis. Orthonormal independent vectors as the basis. Then every A has a unique representation. Every tensor has a unique representation, which is this Aij, Ei, Ej. And as you can see, the primes indicate the corresponding components in the rotated coordinate system. So Aij, Ei, Ej is specific to one particular coordinate system. The same tensor, when you rotate the coordinate system, I am representing with a corresponding prime symbol on each variable. I've written this directly now. How did I get this? Aij is A times Ej dot Ei, and I've rearranged it to write it in this fashion. Likewise, I can do a similar operation, but how did we get this? How did we get this? Right. So let us quickly try to do it. See, we have A is Aij, Ei, Ej, right? Let me write it in big. Let me erase this part. We have A is Aij, Ei hat, Ej hat. Now, either side, I'm going to multiply it with Ej. So I have Aij, which is a scalar, Ei, Ej times Ej. Right? What is this Ei, Ej times Ej? This is basically dyadic product. And how does this simplify? This simplifies as Aij, Ei times Ej dot Ej. This was the definition we have seen how many slides back? Here. This is what we have seen. I'm trying to do the same thing. I'm just applying what we have learned. Okay. And ej dot ej is nothing but delta jj, which is 1. Right. So this becomes aij ei. It's a vector now. And on the right hand side is also a vector. This is what we have. Now I need to know what aij is. So I'll simply take the dot product on either side. So it is dot product, the order does not matter. So I can write it here. Aij ei dot ei. And ei dot ei is 1 anyway. So you get aij is ei dotted with tensor A times A into EJ. How do we evaluate this A into EJ? We will see in a minute. But that is what we are trying to say here. Aij becomes A times EJ dotted with EI. And since it's a dot product, you can as well A dot B is same as B dot A. So that is what it is. This is how we have arrived. It is a simple application of the dyadic product. This is a dyad on a vector, which means take the dot product and you get delta jj here, which means either side, left hand side and right hand side become a vector, and you want to know the component, so you dot it with the same unit vector. That's all we have done. And likewise, this extends to any other coordinate system, not specific to the original basis that you choose. Any basis, provided the space is the same, the Euclidean space is the same, you can extend this notation. The matrix form of evaluating the same is this. Okay. And when we have to take dot product, as you might have, as we have seen earlier, you take the transpose, and this is how it is. So this is how you evaluate the components of a tensor. You have a vector V, the way you identify its x component. How do we identify the vector's x component? Vx is simply V dot I hat. But when it is a tensor, you'll have to take, tensor has 2 suffixes. A vector has only 1 suffix. That's how we distinguish a vector from a tensor. A tensor has 2 suffixes, hence you would end up doing 2 such products. So this is how you identify the component of a tensor, given the original tensor. Right? So let's continue to see what some elementary operations. We have seen one such operation, which is identifying the elements of a tensor given the basis of the space. Right? So what is called, this is called as a post multiplication. So this is something which we have seen here. Here we have a post multiplication as well as we have a pre-multiplication. The first stage, we only have post multiplication, right? A into EJ. How does one evaluate this? It's easy. You can always stick to one notation. This is what we have. B is a tensor A times a vector A. In matrix form, this is what it is, because you know the size of A is 3 by 3 if you stick to matrix notation, and the column vector is 3 by 1. So essentially you get a left hand side also becomes a 3 by 1 matrix, which can be represented as a vector. Now let's try to do this initially. How do we identify just the second component of B or the third component of B? So I'm going to expand this into the initial notation. Instead of writing such big matrix, this happens in one line. I'm going to show it in few lines, mainly because we are all beginners in initial notation. Otherwise, you can write it in by the first look of it. And by the end, by the time in the next minute, most of you would also be in a position to write it, to see and write it. So I've written A in its initial form, which is, that's why EI is the dyadic product. And A is AK times EK. EK is a unit vector. All E hats are unit vectors, right? And AIJ and AK are scalars, so I'll group them together. And EIEJ times EK, that's basically the dyadic product. And hence I can simplify this as EJ dot EK. That's how we define the dyadic product. And EJ dot EK is nothing but delta JK, which is a scalar, right? So far good. And delta JK is a Kronecker delta, and this will survive only when J equals K. And since I have AIJ, I will simply make AK as AJ, right? And I basically have this AIJ, which is a scalar, AJ is another scalar, times EI, which is a vector. So this operation tensor A into vector A has given me a scalar. So in other words, in initial notation, Bi is nothing but Aij Aj. All right, Bi is Aij Aj. And even by now, you perhaps, being familiar with matrices, you can as well write this by just looking at the very first expression. Some of you may be in a position to do it, which is good. Or else now you have the proof of it. Let's do the same similar operation, but we'll do a pre-multiplication. So this is what I have. Again, please do not combine. This is something which has occurred due to a different kind of package I've used in LaTeX. Please keep the under arrows separately, underlines separately. In matrix form, this is what it is. So you're essentially doing A transpose times A. A transpose is 1 by 3, A is 3 by 3. Right? And let's work it out using initial notation. This is what we have, A times A. And I'm using the same, expressing A in initial form and the tensor also in terms of its dyads. So again, same style, nothing changes. I'm taking the tensor product, EI, EK, EI, EJ. So EK, it becomes EK dot EI because it's a pre-multiplication. So it's the first two terms which get the first two vectors which are dotted together. And the dot product leads to a Kronecker delta, and it survives only when both its indices are equal. I am essentially going to replace K with I. And that's what we have done. And you can see the initial notation is nothing but Bi is Ai times Aij. It's the other way. Right? So this is how you do a pre-multiplication. Now the expressions are all two terms. Soon we will get divergence, gradient, Laplacian, all those things. So that's when this becomes very handy, both these expressions. The one we have seen in post multiplication and the ones we just saw in pre-multiplication. All right. So now we have seen three kinds. One is evaluating the components of a tensor given its Euclid's 3D space. The second is post multiplication. The third is pre-multiplication. Right? Let us define one more, which is called as a tensor product. Multiplying two tensors, there are two ways you do it. One is what is called as an inner product, which we will see in a handout. And the first one is the tensor product, which is shown here. It is shown like a dot product. A tensor product leads to one more tensor. It's like, think of multiplying two matrices, both of which are of the size 3 by 3. Often some books also ignore the dot sign in between and simply write it as the way we have shown, but do not put a combined underline. That has happened, as I mentioned, due to a different package that was used. Okay, this is what it is. Right? This is the tensor form of a tensor product. How do you do it? I'm expanding it. A, I can write it in terms of its dyad. B, I can write it in terms of its dyad. Right? And then you know the drill. Ei, Ej times Ek, El. So this is like a dyad acting on this vector. So this is what it becomes, Ej dot Ek. Okay, and this survives only when this becomes, since these are unit vectors, this become the Kronecker delta with suffix jk, and this will survive only when j is equals to k. So this becomes j is equals to k. And further, there is no other simplification. In fact, this is how you multiply matrices that you see. Okay, so this is the ILth component of the tensor AB. This is the new tensor you have. Its ILth component is this. Okay, since by now you know K is a dummy variable. I and L are the free indices. K is the dummy variable or also the repeated variable here. This is it is on the variable K that we will sum up. All right, so this is how a tensor product is defined. So now we have seen 4 of such operations. And the last thing, we have seen what happens to a vector when it is being rotated. Now let us try to do the same thing now we have the left hand side figure is showing a particular right hand coordinate system whose unit vectors are E1, E2, E3. E1, E2, E3 need not be I cap, J cap, and K cap. Okay, you can have any such given a Cartesian space, you can have any three orthonormal vectors as your basis. So there is a tensor in the left hand side coordinate system, and the coordinate system is rotated. Okay, and we want to write that particular tensor in the rotated coordinate system. That's what we want to do. This is the original, and that's a rotated one. So the tensor as such remains the same, but its corresponding components will change. So in the original coordinate system, the diode is represented by EI, EJ. Whereas in the rotated coordinate system, it is EI prime, EJ prime. We need to identify the scalar component, which is A suffix ij prime. Everything is known. We know the original tensor, which means we know all this. And now we have rotated the coordinate systems, which means we know the position, we know the orientations of the new basis. Rather, the old, we know the orientation of the basis with respect to the original basis. It's not a new basis. It's just that the old basis vectors have undergone a rotation. So we know EI prime and EJ prime. We need to identify what EIJ prime is. So that's what I've tried to write. All components in the first coordinate system are known, and the unit vectors in the rotated components are also known, and Aij needs to be determined. So this is what we have. The tensor remains the same. It's just that its components vary. Right. So what do we know? We know only one. We know only a couple of operations now. One is the tensor product, and the second is the pre-multiplication or the post-multiplication or the dot products. Right. So let's do the same. So I am multiplying both sides with some vector, some unit vector in the rotated coordinate system, which is EQ prime. Right. And on the left hand side, we can take the dyadic product, right? Which means it becomes EJ prime dot EQ prime. Right. Likewise, on the right hand side, it becomes EJ into EQ prime. If you recall, this EQ prime dot EJ on the left hand side can be written as QIJ. Right? QIJ, this is how we define. So I'm going to write it this way. So I'll have the left hand side in a much pleasing manner. The right hand side is it simplifies to that Kronecker delta JQ. Right? And now I'm going to take I want to identify the scalar component A prime IJ, rather Aij prime. So now I'm this right hand side survives only when J becomes Q. So this is the last expression that we have in the previous slide, right? And I'm writing the same thing again. So I've just rewritten the left hand side. I've interchanged the left and the right hand side, and I've got rid of the Kronecker delta by eliminating the zero terms. So I'm left with AIQ EI prime. And now I need to take the dot product with some vector in the rotated coordinate system. With the time, you will skip all these steps and you may write all of them, but I thought we will do everything in detail. So I'm multiplying, I'm taking a dot product with a vector in the new, with a unit vector in the rotated coordinate system. And again, you get a delta IP, right? And likewise, the right hand side will again simplify to that transformation matrix. And this is how you get. Okay. And delta IP survives when only I equals P. So you have the new components of the tensor as this. And from matrix algebra, you know, like, you know, CD is Cij into djk and C transpose is this. So basically, you know how a transpose changes things. I'm going to use the same concept in the last expression that we have here. It's not incorrect to leave it this way, just that I'm trying to make it look better. Okay, so this is what you have. I have rearranged the terms, and using that notation which we have, this is how you end up with. And hence your final initial form becomes this. Or in matrix form, this is what it is. Okay. If it was a vector, if you can recall for your vectors, this is what you had. V was the original component and Q was the transformation matrix, and that's how you get the new components. So, but when it's a tensor, you have a transpose here and all this. You have an additional transpose. All right. So essentially, whatever is shown in this slide, or rather this one and the last one, or the corresponding initial notations, are called as a transformation laws for vectors and tensors. Transformation with respect to a rotated coordinate system. Transformation of the components, to be specific. We are identifying what are the components of the vector or the tensor in the rotated coordinate system. Okay, in dynamics, you will rotate the body. In most of the other branches of mechanics, we will rotate the coordinate system, mainly because the objects are static, or a bulk of the analysis is simplified to a static analysis. You can as well simplify a dynamic problem to a static problem. We might solve a couple of problems as we go towards the end of the course. A little more on transformations. I can write the same previous expression, the very first expression on this slide. I'm writing the same expression in terms of the partial differentials. In fact, that's what it is. If you recollect if you can rewind your previous lecture, you can see how Qij was defined. How did we arrive at this? Just so that let me erase this because we have something else coming up here. This is what we have. We had x prime I prime dot plus y prime j prime dot plus z prime k prime dot. Z prime k prime is equals to x I hat plus y j plus z k. And then we started taking dot product with, first we started with I prime, right? So it's basically, that's what you are getting. That is how you get this. Okay, this is not anything which you have not seen. This is coming from this particular expression only after taking the dot products. Right? You can extend some such analysis to a fourth order tensor. How do we deal with things for a third order tensor? Something which you guys can work as a homework. But a fourth order tensor is, you can do similar such extensions. What is a quick application that we can think of? Is a stress transformation that we have seen often in mechanics of solids. So you might have used Mohr circle, but one can as well use this. For example, in a 2D problem, you have only 3 unique components of stress. And if you rotate the coordinate system, you can construct your corresponding Q matrix as this, and then identify the matrix, identify the new components. Okay, it's one shot in if you use this matrix notation or tensor notation. Okay, whereas you can remember this formula, but it always helps if you can put it in a nice tensor or a matrix form. Right, and some things we'll wind up this part of this lecture with some standard things which we must all be aware of, which is on symmetric and axis anti-symmetric tensors. So if you take a transpose of a second order tensor, and if it is equal to the original tensor, then it is called as a symmetric tensor. And you can see it has only 6 unique components. Okay, let me try to circle it. 1, 2, 3, 4, 5, 6. Or some people simply show this and write nothing but symmetric here. Okay, there are essentially 6 independent components. For an antisymmetric tensor, if the transpose adds up with the original tensor and it becomes null, then such a tensor is an antisymmetric tensor. And here the unique number of components are just 3. And since there are just 3 components, people thought, okay, why not I represent this as a cross product matrix? And if you carefully observe the notation of this, it boils down to that cross product matrix which you have seen in dynamics course. So an axial vector was coined out of this. Okay, and it comprises, so if A is an axial vector of an antisymmetric tensor, then the following should hold true. Okay, what is the corresponding axial vector here? A12, A13, A23. Okay, depending on which book you're using, some order may get interchanged. That's all right, but end of the day, it boils down to this. Okay, axial vector is mathematically, this is how it is derived. In fact, this is how you can identify what A is, what are the components of small a from this particular definition. So accordingly, you can actually correct what your vector is. All right. So that is it with respect to this lecture. But end of this lecture, I'm going to upload a handout which talks about the transformation properties of not specifically transformation alone, all operations similar to a vector algebra. I will upload an handout which is about 3 to 4 pages, and it has all operations such as closure property of tensors, basically saying tensor A plus tensor B, if it is equals to another tensor, then the commutative property tensor A plus tensor B is nothing but tensor B plus tensor A, and then the associative, which means the order does not matter when you add tensor A plus tensor B plus tensor C, is you add A plus B together or A plus C together and then add it to B or C accordingly. So properties or mathematics which you are very familiar with, I thought I would summarize that as a handout, and I've uploaded that particular handout on MOOCit. Okay, so you can go through those operations, those standard properties, and my suggestion is that you write them in terms of indicial notation. Okay, that will be a very good practice towards your first phase of the homework. All right. So we will meet in the next class when we look at the tensor functions. What exactly is a tensor function? So we will see what tensor functions are, what vector functions are, or vector valued functions, vector valued scalar functions, and so on. All right. So I'll see you guys in the next lecture when we work on tensor functions.